Hello there, this is Alana Tucky, and this is going to be a tutorial for section 8.1, number 22. So let's see here. Let's suppose a geyser has a mean time between eruptions of 110 minutes. Let the interval of time between the eruptions be normally distributed with a standard deviation of 40 minutes. Complete parts A through E below. Okay, so before I even get started, I noticed here that it says the interval of time between eruptions is normally distributed with a standard deviation of 40. That means that it's normally distributed flat out. So n could be 1, n, your sample size, could be 2, n could be 3, n could be 4, n could be 37. It doesn't matter. It's going to be normally distributed no matter what. So then it asks in question A, what is the probability that a randomly selected time interval between eruptions is longer than 120 minutes? Okay. So bear with me because I've already done this entire video once and my computer ate it. So n is equal to 1 because it said the random time between eruptions is normal, right? That's what it said. Then it said mu is equal to 110 and sigma was equal to 40, right? Mu being your mean, sigma being your standard deviation. Okay? Okay, so then we can go find this with StatCrunch. So let me pull up StatCrunch. Go to Stat, Calculators, Normal. All right, the mean was 110. Standard deviation was 40. Now remember that keep these two straight. This part inside the parentheses, that's the vertical bar, and this part over here is the area. Well, we have the vertical bar, it's 120, but I want to be longer than 120. I want to know if I'm going to have to wait more than 120 minutes for this flippin' geyser to erupt, right? Okay, so got my geyser, there's my chances. So if I'm sitting there for a single eruption, the chances of waiting 120 minutes or more for the geyser to erupt is 0.4013. All right, so then I take a picture of it and I paste it into here, and there it is, 0.4013. Now, if I want to do that with a calculator, it's no big deal. So I would just grab my calculator. Sorry, I already did this. So second distribution, hit number 2 or go down and press enter. Either way it'll work. And you can see I have 120 because that's the left-hand edge. You see right there, that's 120. So that's the left-hand edge of what we're shading. And then the right-hand edge is forever because it goes on forever. But the calculator doesn't handle forever. So it's going to say 1E99. And then the mu is 110. And the standard deviation is just 40 because you're talking about a single. And then paste, enter. And there you have it. So that's how to do it with a calculator and how to do it with StatCrunch. Remember, at this point, we basically abandon Excel wholesale because it's just not going to do for us what we need it to do. Not easily, at least. All right, so now, what about Part B? Part B is going to talk about, first I'll prove to you that I was right about Part A. There it is, 0.4013. Now, what's the probability that a random sample of 40 time intervals between eruptions has a mean longer than 120? All right, so that's not you sitting there with your family for one eruption waiting longer than 120 minutes. It's you sitting by Old Faithful for 40 different eruptions. What's the chances the average of those 40 different eruptions would be longer than 120 minutes? Okay, so it's all going to be basically the same, except what's happening is that your standard deviation is different. So your standard deviation, instead of being 40, is now the standard deviation of the sampling distribution. So you have your mean of your sampling distribution, which is still the mean, which is 110. But your standard deviation of the sampling distribution of the sample means is something called the standard error. So it's faster than saying the other thing, which is sigma over the square root of n. We learned that in the central limit theorem in 8.1. So that's 40 divided by the square root of 40 this time because my sample size was 40, which I used in my calculator, and I found that's about 6.325. If you want to see it, here I can show you. 40 divide by square root, which is above the x squared button, 40, enter, and there you have it. Okay, so then it's about 6.325. So when I go to StatCrunch, it's going to be the same thing I did already, but I'm going to tell it, instead of 40, I'm going to tell it 6.325 and click compute. And there you have it. Okay. So each standard deviation is now worth about 6.3 as opposed to 40, right? So 2 standard deviations away, 2 standard errors away is 122.6. So it's much, much further than it was before. So then I pasted that in, and you can see that you're still talking about 120, but 120 for a single is very close to the mean. 120 for a group like this is far from the mean. And then that gives you this value right here, 0.0569. Now, if you do it with a calculator, you have a couple ways to go. So I go second distribution, number 2. You can either just hit the number 2 or you can go down and press enter, either way. All right, 120 is still good, 1E99, everything's good, but here. Now you could do 6.325, or you can actually type 40 divided by second square root 40. This will actually be more accurate. And then go to paste and press enter. And you can see it's got a little bit more decimal places of accuracy down here. Well, you wouldn't know it's accurate, but it is. See how they're both 0.0569, but at that point this one becomes 3586 and this one's 2315. That's because the one on the right with the calculator is more accurate because it didn't round to 6.325. It kept lots of decimal places for that standard error value. But either way, it's about 0.0569 for the answer. So when you're talking about a single eruption, you're just sitting there waiting for the eruption to go, the chances of you having to wait longer than 120 minutes, longer than 2 hours, is 40% for a single eruption. But if you took 40 random eruptions and got their average, the chances that the average of those eruptions being over 120 is very small, 0.0569. All right, now for part C, look, there's a 6.325, just like I said, 0.0569. I'm not going crazy. For part C, they want to talk about the random sample of 100 time intervals. So you're not talking about 40 eruptions, you're talking about 100 random eruptions. They're not even in a row, it's just 100 random eruptions. What are the chances that you're going to have to wait that long? So let me set this up. All right, so your standard error is not going to be 40 over the square root of 40 anymore. It's going to be 40 over the square root of 100. Square root of 100 last time I looked was 10, so this is 4. I can do this one in my head. All right, so we've got 4. So then what I'm going to do with StatCrunch is I'm going to change this to 4. Click Compute. I like the other tick marks better. There we go. I copied and pasted it right here, and there you have it. And then if you don't have StatCrunch, you have your calculator, that's fine. Second distribution, number 2, fine. And down here, instead of all that, you're going to say 4. Enter. And these will be identical because neither one of them is rounded because 4 is a rational number, right? So we're set. And there we have it. So 0.0062 is our answer. All right, now if you didn't notice it, did you notice how much smaller that is? Every single one of these problems is talking about 120 minutes and over, 120 minutes and over, 120 minutes and over. But where 120 is further and further and further away from the mean. The mean is 110, but because of the central limit theorem, as we get a larger sample, then what a standard error is worth gets smaller and smaller. So when you're talking about a sample size of 1, the standard deviation is 40. But when you're talking about a sample size of 40, the sample standard deviation is 6.325, i.e. the standard error. That's why the tick mark here happens at 6.3. Down here, it's going to happen at 4. So there's 4, that's one standard deviation, standard error. There's 8, so that's the second standard error. And there's 12, that's the third standard error. And 120 is getting further and further and further. Even though it's still 120, but how many standard deviations of the sampling distribution of sample means it's worth, it changes. So this means that it is much harder, it has a lower probability to have a group of times between eruptions have an average that's over 120 minutes. It's much easier, and you can say this is because the standard error is much smaller for a group of size 100 than a group of size 1, or 40 for that matter. It's much easier to have a single time that's 120 minutes. Like if you go to, say this was Old Faithful, if you're going to go sit at Old Faithful, it's not unheard of for you to have to wait over 2 hours, over 120 minutes. The chances of you having to wait over 2 hours is 40%. But the chances of 100 different eruptions of Old Faithful having more than 120 minutes as their average between eruptions is very, very small, 0.0062, right? And it's because a group balances out its highs and lows. So it's hard to have a lot of extremes, right? To have a group have an average that's that high, basically the whole group would have to be quite high. And if it's truly normally distributed, that's not going to happen. You're going to get some below 110 and some above 110. But to have a group of 100 have an average that's 120 means that they were all basically around that high, which would be unusual in the extreme, right? That's what I'm writing here, right? Basically, it's going to be hard to have a group that's that high. You can have a single eruption, sure. I mean, you go to wait, you might wait over the 120 minutes for any one particular eruption, but you're not going to have a group of 100 have an average of over 120. It's just not going to happen. Well, I shouldn't say that. What might you conclude if it does happen? Well, there's a lot of options. One, it could just happen. I mean, I shouldn't say it doesn't happen. It does, but it's very rare. Right? The probability of it is 0.0062. So, stuff happens. Sometimes you get just random fluke. It's just going to be really long waiting times. It occurs, but it's only going to occur 0.0062, right? Or which is 0.62% of the time. Very, very small. It could be that you were biased somehow. Let's say you only took your readings, I don't know, in the middle of the day, and maybe for whatever reason, the middle of the day, it takes longer between eruptions. Or you only did it in June, but for some reason January is shorter, or February, then something like that. You biased yourself in how you took the sample. That's possible. Or, and what we're setting you up here for is chapters 9 and 10. So if these two are out of the picture, if you say, look, it's not a bias sample and I think this is too low to be a random fluke, then what's the other option? And the other option is that it's not what you thought it was. So you thought that the mean was 110, the sigma was 40, but maybe that's wrong and it's no longer holding true. Maybe that was true 10 years ago, but Old Faithful has changed and now it's something else, right? This is how you start proving, quote unquote, because we don't ever really prove anything, but we're proving that it's likely that these parameters are wrong and that it's something else. Maybe it's higher, maybe it's 115 now or something like that. All right, I hope that helps with that question. I'll see you back here for more tutorials.